It says find the domain of each rational function. What it's saying is what are the x values that cannot go in to the denominator, basically. So we're looking at denominators for rational functions. So we would set our x squared equal to 0, and we would say x equals 0 cannot go in the denominator. Okay, so you can write out your domain in two different ways. So the easiest way, and the way that I think you guys will probably prefer, is to say x is not equal to 0. Totally fine. If you wanted to write it in the more complicated way, you could do interval notation, which is -infinity to 0, union 0 to infinity. Okay, so you could also write it out that way. Which way is easier? The first way, right? X is not equal to 0. All right, so on the next one, we would factor, and you can factor both the numerator and denominator if you want. And the denominator factors into x minus 1 times x plus 4. And so nothing cancels. So when we talk about our domain, we say, oh, well, we can't have two values in the denominator. So our denominator, x minus 1 times x plus 4 equals 0. We can't have x equals 1, and we can't have x equals -4. So our domain, we would write x is not equal to 1, and x is not equal to -4. That's the easiest way of writing it.
Can we just write x is not equal to 1, comma -4?
Yeah, you could just put not equal to 1, comma -4. Okay, so when you write that, you're assuming that they're real numbers. So it's all real numbers except for these two. Okay, easy enough. So what does this do on our graph? Well, this basically creates our vertical asymptotes. So it says the line x equals a is a vertical asymptote if a is not in the domain of the function. In other words, a makes the denominator 0. Okay, so there can be exceptions, and we're going to talk about that in a little bit. It's when we have something called a hole. Okay, so if something had canceled here, like if I had my x plus 1 and my x, let's say I had an x plus 1 on the bottom and they had canceled, that actually won't create a vertical asymptote. That creates something called a hole. So we'll talk about that in a second. Okay, so let's start with this. So it says find the vertical asymptote for f of x equals 3x over 2x plus 5. So in order to find a vertical asymptote, all we're going to do is we're going to set our denominator equal to 0. So we're going to say 2x plus 5 equals 0, and we solve it out. So we have 2x equals -5. So x equals -5 over 2. Okay, so -5 over 2 is -2.5. So on our graph, we would go over to -2.5, and we would have a vertical line that we're not going to cross. Okay, and you could do a t-table to find some other values. But basically, you could have something like this, and it goes along there. You could have something like this, it goes along. So we don't know exactly what it's doing yet. We're going to talk about how to graph these by the end of this section. Okay. So that's what a vertical asymptote is. It just gets closer and closer and closer, and it doesn't cross that line. All right, so a horizontal asymptote. So for some reason my steps got cut off. This should all be in one big box. It says the line y equals b is a horizontal asymptote if the ends of the graph get close to the line, but they don't cross the line. So for a horizontal asymptote, you can actually cross it, okay, except not on the ends of the graph. So you might have things where you have a vertical asymptote on both sides, and then maybe you have a horizontal asymptote somewhere. And maybe on the right side and left side of the graph, we don't touch that horizontal asymptote. So I know I made mine look like it crosses, but it just goes up along that horizontal asymptote. But in the middle, it can actually cross. So you could have something like a cubic function, like what looks like a cubic function in the middle. So just on the ends of the graph, we're not crossing there, okay? It's very much like end behavior. Do you guys remember end behavior? So what are the 4 different conditions we had for end behavior? So we could have both up, both down, or what Maury calls the John Travolta, right? 1 up, 1 down, right? So those were the 4 different conditions. Well, what about things that don't go up or down? Like what if they just kind of go out? That's what this is. Okay, so horizontal asymptotes just kind of go along a horizontal line. So there are 2 ways to finding the horizontal asymptote. So we're going to do the long way and the short way. Once you guys do the long way one time, you're going to be like, oh, now I see why there's a shortcut. It's not like super long, but you'll understand this, okay? So here's the long way. Okay, you ready for this? Our steps, we're going to look for our largest degree. So in the numerator and denominator, what's our highest power? 2. So we're going to take every single term, and we're going to divide everything by x squared. Where do we get that? and then we're going to simplify it. So we're going to say, okay, 10x squared over x squared is 10. 2x over x squared is 2 over x. 15 over x squared is 15 over x squared. And on the bottom we have 5 plus 3 over x squared. So I just told you that for horizontal asymptotes, we're talking about the end behavior. So we're talking about if I plugged in a really, really big positive number, right? Remember how we would write out as x goes to infinity, y goes to blank. Do you guys remember that? So imagine I plug in a really huge number, like 1 million. What happens when I plug in 1 million right here? So if I have 2 divided by 1 million, what is it close to? 0. What if I plugged in 13 trillion? 2 divided by 13 trillion, is that even closer to 0?
Yes.
Yeah, it is. Does this make sense? So the bigger you get on the bottom, the closer that result is to 0. So that's what's using something that we call a limit. So in calculus, you might see things that say like limit as x goes to infinity. We're not going to write that out. We're just going to assume that we're plugging in a really, really big number, and we're going to say, well, what happens to it when I plug in a big number? I always give the analogy, this is gross, but pizza, whenever we talk about fractions, we always talk about pizza. Welcome to American math. I don't know why we do this. So if I had 2 pizzas and I divided into 4 people, then I have one half of a pizza for each person, right? So if you had 2 pizzas and you divided by 13 trillion people, how much of the pizza do you have? You don't have anything, right? You're like barely eating anything of pizza. It's like, it's gross, but it's like you're licking the pizza and you're passing it on to someone else, right? That's how much pizza you're getting. You're getting nothing. All right, so 2 divided by a really huge number goes to 0. So that means this is going to go to 0, this is going to get closer and closer to 0, and this gets closer and closer to 0. So what are we left with? 10 over 5. And what is 10 over 5, Caleb? No. 2 over 1, right, so it's 2. So that would be our vertical asymptote, or sorry, not vertical, horizontal asymptote, y equals 2. Okay, so looking at the original, can we shortcut that process? Yeah.
Why exactly did you cancel out everything with an x or x squared?
Because we're saying, like, if I had a big t table and I was plugging in a really huge number for x, what would this all be close to? These terms become insignificant. They're like so small that they don't matter.
That's why we were talking about the huge number. I wasn't sure why we were. I mean,
Yeah.
I understood it was very close to
Yeah.
0, but I didn't understand
Why we were plugging in those numbers.
why we were doing it.
And same with a negative. If you plug in a negative big number, same thing happens, right? So on both sides, we go towards 2. So we're not going up, like up or down, right? We're just going towards that horizontal line 2. So it's like this on the ends. So we're getting closer and closer to it. And we could be coming from the top or the bottom. All right, so the shortcuts. There has to be a way we can shortcut this. So let's think about our largest degree. So our largest degree was x squared, right? So if I look at my original problem, and I know that anything that has a smaller degree is going to go to 0 anyway when I do the process, the long process. Yeah, I just don't worry about those. They're going to go to 0 anyway. So when I have 10x squared over 5x squared, what is that? 2. So we get y equals 2. Isn't that easier? So a lot of times you can just look at a function, you can be like, oh, the largest degree is x squared, 10 divided by 5, 10 divided by 5 is 2. Done. Horizontal asymptote. Okay, so let's try some other examples, some weird examples. So this next one, what's our largest degree in either the numerator or denominator? X cubed. We don't have an x cubed. So all we do is we put it in. We say 0x cubed plus 2x squared plus 50x, or plus 50, I guess, all over 4x cubed minus x minus 1, and we look for our largest degree, and we divide them out. So when I divide 0 over 4, what do I get? 0. So y equals 0 is my horizontal asymptote. Done. So what's the logical question that comes after that? What if it was bigger in the numerator than in the denominator, right? So that's what example number 3 is. So what if it is bigger in the numerator than the denominator? So this is our largest degree. That means we would have 2x to the 5th plus a bunch of stuff. And on the bottom, we would have 0x to the 5th, right? So when I look at 2 divided by 0, What is 2 divided by 0?
Undefined.
It's not, it doesn't work. The trick is 0 over k is okay, that's allowed, that's 0. N over O is no, that one's not allowed. Do you guys like that? All right, so it's undefined. So what do you think that means about a horizontal asymptote?
There isn't one.
There isn't one, so we write no horizontal asymptote. Okay, easy enough? The cheesy way of remembering, I have lots of ways for you to remember silly things, but is to remember the difference between a horizontal asymptote and a vertical asymptote. The horizontal asymptote is ha, H-A, right? Horizontal asymptote. Ha, there's a shortcut. That's the one that has the shortcut. So you're looking for that shortcut. I know, you think it's silly, but on the test you're going to be like, ha, there's a shortcut. Okay, got it. All right, so holes. So sometimes there are values that make the denominator equal to 0, but they are canceled when we factor the numerator and denominator because there's a common factor. Okay, so if you can't input a value into the original function, then we still say that it's undefined there. So there's a hole. Sometimes we call these point discontinuities or removable discontinuities. So I won't call them that. I'll just call them holes in Algebra 2. So here's an example. So I think all of you guys are going to understand this concept. So looking at f of x equals x squared minus 4 over x minus 2. Who can I call him? Lucy, what do you think? X squared minus 4 over x minus 2. What do you notice about that? Yeah, you can factor it. X minus 2, x plus 2. And when you do that, the x minus 2's cancel. Right? You guys were pros at 9.1. Most of you guys did pretty well in that section. You know how to do this. You know how to factor. You know how to break it apart. And reduce. So it reduces to x plus 2. So we're going to talk about the simplified function. So our simplified function is f of x equals x plus 2. Or instead of f of x, I'm just going to write y because I think it will make more sense to you guys. So if I have y equals x plus 2, is that a circle, parabola? It's just a line, right? It's a line with slope of 1, y-intercept of 2. So we go up to 2. We go up 1, right 1, up 1, right 1. And we get this line. So our original function is pretty much equivalent to that, except for one thing. So if, in the original function, I decided that I wanted to graph it using a t-table, what happens when I plug in 2?
You get undefined.
Yeah, I get 0 over 0, right? Which is undefined. It's not 0, it's undefined, right?
But isn't 0, that counts as undefined?
0 over 0 is undefined, yep.
I thought that just...
Yep. Anything divided by 0 is undefined. So that means that we can't have, what point is this right here? We had 2 comma what? We went up 1, right 1, up 1, right 1, 2 comma 4. We can't have that point there. We don't plug in 2 and get 4. So what do you think we do?
Get rid of it.
Get rid of it. It just goes away. It's just like a little thing there. Pretty much, right? So it's pretty much like that. It's just a big hole there. So there's no point there at 2 comma 4. It jumps over it. Yeah.
Wait, do you mean like when we plug x in for the original problem?
Uh-huh.
Oh, okay.
Yeah, if you plug it in for the simplified, you do get 4, right?
Mm-hmm.
So it's clear that there's something happening at that point 2 comma 4, but in the original it was undefined. Jacob, what are you doing? There's lots of giggles back there. Manish and Jacob. Are you guys writing notes to each other? I never find any juicy notes in my classrooms these days. Back when I first started teaching, people didn't have cell phones because that's how old I am. And I would find juicy notes. I would know all the gossip in the school because I'd find notes everywhere. But now it's on your phones. And I refuse to look at the phones when people leave them. I don't want to know. All right, so here we go. So f of x equals x minus 3 over x squared minus 5x plus 6. That was a hole. Okay, so let's see if this one has a hole as well. So we're going to factor the numerator and denominator. So the numerator is still x minus 3. The denominator factors into x minus 3 and x minus 2. So there's a hole, right? So when it cancels like that, that's where we're going to write there's a hole at, and we think about what x value made it 0 over 0. So what did you plug in for x to get 0 over 0? 3. Do you guys see that it's 3? Do you guys see how 3 minus 3 over 3 minus 3 gives you 0 over 0? So let's write that up here. So I didn't write that on the one above. When I simplified it, there's a hole at, so what makes it 0 over 0? What would I plug in for x? 2, right? 2 minus 2 over 2 minus 2 is 0 over 0.
If it was positive and then it was negative.
Yeah, so it was like x plus 2 would be negative 2 would be the whole. All right, so our simplified function now is not y equals x minus 2. It's y equals,
1 over x minus 2.
yeah, it's a 1 over x minus 2. And that's what we're going to graph.
Why is it a 1?
Because the top went away, right? So when it goes away, we write a 1 on top. Just like normal fractions, like if you reduce out, like 2 over 4. Like if you had 2 over 4, it becomes a 1, right? If it goes away. Okay, so this is a little bit tricky. This is the first rational function that we're going to graph. So we're going to go through a lot of steps. I want you to tell me the horizontal asymptote and vertical asymptote. So let's start with vertical asymptote. In order to find the vertical asymptote, I set the denominator equal to 0. Are you writing a note? You're going to fold it up all cute. So if I set my denominator equal to 0, I'm going to have x minus 2 is equal to 0. Yeah? That's probably yours, I'm sure. It matches the one that you have already. So x equals 2 is our vertical asymptote. All right, our horizontal asymptote. There's a shortcut, right? That's our shortcut method. And notice how I'm just using the simplified version. I don't go back to the original, I just use this. So our biggest degree in that one is x the first. So we have no x the first on top, and we have 1 x the first on the bottom. So we get 0 over 1, which is 0. So y equals 0 is our horizontal asymptote. It's always hard to draw y equals 0. It's like right on top of that line. And we could find other things. Do you guys remember finding x-intercepts and y-intercepts when we were graphing lines? Yeah, to find an x-intercept, we plug in 0 for y. To find a y-intercept, we plug in 0 for x. A y-intercept's always an easy one to do. So what do I get when I plug in 0 for x?
Negative 1/2.
1 over negative 2, so negative 1/2. So I know that it's crossing like right here. But if I didn't know that, other good points to plug in, and we just do a quick table, are ones that are on the left and the right of the vertical asymptote. So our vertical asymptote's at 2, right? So what's on the left of it? 1. So can you guys pretty quickly plug in 1 for x? 1 over 1 minus 2. So 1 over 1 minus 2 is negative 1, right? So when I plug in 1, I get negative 1. And when I plug in the thing on the right of the vertical asymptote, when I plug in 3, what do we get there? 1. And really, that's enough to know exactly what this graph looks like. So I know this is the first time you guys have graphed it, so it's like a little bit weird. But remember, horizontal asymptotes we can cross, but vertical we can't. So it's going to go along the vertical, and then along that horizontal in the end, and then along the vertical and then the horizontal. Yeah?
Okay, I'm sorry. I don't understand why, like, it's 0x to the first. Over
0x, oh, how I got the horizontal asymptote?
Yeah.
Okay, so remember horizontal asymptotes, I said, there's a shortcut. So we do our shortcut method, which is looking for our largest degree. So when we have 1 here, that's like no x values and a 1. And then x minus 2 is 1x minus 2. So we're going to do 0x over 1x. You're writing it in like a descending powers, like you're looking for your largest degree. You could go back to the original too if you want to. So you could go back here and you could say, oh, I have 0x squared over 1x squared, and it gives you the same thing. All right, and then our very last step, remember there's a hole at 3. So we had a point at 3 based on the simplified one, but it's not actually there. It's gone. So we just have a hole right there. So don't forget that at the very end. So there's a hole at x equals 3. Okay, does that make sense?
Why is there a hole at 3?
Because in the original function, if you plugged in 3, you would get 0 over 0 because of that. So you can't have a point there because 0 over 0 is nothing. It's undefined. No point there. All right. So one more thing before we graph this, we do all this together. So the last thing is a slant asymptote. Okay, so sometimes asymptotes aren't like straight up and down or straight left and right. So sometimes they look like something like this. That would be a slant asymptote. And usually those go along with a vertical asymptote. And it's usually like this is how we would draw the shape, okay? Sometimes it could be these ones over here, but usually it's in the smaller one. Okay, so notice how it says, so it says if the degree of the numerator is exactly 1 more than the degree of the denominator. So like this was degree 2, and this one is degree 1. It's a weird one. So 1 more on top. So look for slant. So I'm not going to say that every single time this happens there's a slant asymptote, but a lot of times. Okay, but we've done one example so far where there wasn't a slant asymptote. So let me kind of go back in time. So looking at this one, number 1, do you guys see how we had x squared minus 4 over x minus 2? Well, that's 1 degree bigger on the top than it is on the bottom. But did I get a slant asymptote in the end? No, I just got this like solid line except for that hole. Right, so sometimes it just creates like a line with a hole on it, but sometimes it doesn't, okay? So when would it create that line with a hole on it? When you factor and you can remove those common factors. That's when it would be the line with a hole, okay? But if you try to factor, so let's say I factor the numerator and denominator on this one. Notice how nothing cancels. So that means there's no hole, and there's definitely a slant asymptote. Definitely. Okay. So what does it say? It says that we can find this using, oh, your favorite, long division. So we can find the slant asymptote using long division. You could also do synthetic division, no big deal. So let's say I set this up with long division. I have x squared plus 5x plus 4, and I want to divide by x minus 3. Manisha's looking at me like, for reals? I left for 1 second and we're doing long division? So I say, what do I multiply x by in order to get x squared? X, right? So I put an x on top. I take that x and I multiply by both things. So x times x gives me x squared. X times negative 3 gives me negative 3x. Do you guys remember what I always say? Draw the line. Change the signs. You're going to say that like every time you do long division in the future. Draw the line, change the signs. Add straight down, so I get 8x, and I drop that plus 4. Here we go, one more time. So we say, what do we multiply x by in order to get 8x? 8. So we do plus 8. And we take the 8 times the x minus 3. So 8 times x minus 3 is going to be 8x minus 24. And we draw the line, change the signs, right? Once you get to here, it doesn't actually matter what the 20 or that the remainder is 28. This right here is the slant asymptote. So it's y equals x plus 8 is the slant asymptote. The 28, it's just going to be nothing for us. We're not going to deal with it. All right, so how do we graph y equals x, or y equals x plus 8? We go up to 8. The y-intercept is 8. And then our slope is 1. So we go up 1, right 1, up 1, right 1. And when we do, we create this dotted line. It's an asymptote, right? So we're going to dot it. All right, so let's see if we have any other things. Do we have a vertical asymptote? Yeah, so we set our denominator equal to 0. So we have x minus 3 equals 0. So I get x equals 3. So we definitely have a vertical asymptote. So we create that like X shape. Do we have a horizontal asymptote? That's the slant asymptote. What about a horizontal? So remember how the shortcut? Largest 3 is x squared. I have 1x squared over 0x squared. 1 over 0 is undefined. So no horizontal. Will I ever have a horizontal if I have a slant? I won't, because the degree on top is always bigger if you have a slant asymptote, you're not going to have a horizontal asymptote. So no horizontal. So let's do that thing that I did before where I plug in something on the left and right of the vertical asymptote. So let's plug in 2 and let's plug in 4 to figure out what's happening. Okay, so let's say I plug in a 2. If you plug in 2 into either the original or this factored form, it doesn't matter. You get 6 times 3, 18 over negative 1. Negative 18, is that right? So way down there. That point is actually enough because it tells us that it's going to go along that vertical asymptote. It's going to go up, 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 and it's going to turn and go along the slant. Now, if you wanted to find things like the y-intercept would be easy to do. Can you guys do the y-intercept? Plug in 0 for x. What do you get when you plug in 0? Negative 4/3, which is negative 1.333, right? So that would be somewhere in here. So that kind of tells us where we're turning. We're turning a little bit early. And then we're going to go along that. Now I would say like 99 times out of 100, it's going to be in this other spot here. But let's talk about one spot it definitely cannot be in. So it could be here. It could be here. That's where I was saying 99 times it is there. It can never be here for the other piece. Why can it not be above that other part? Yeah, good thinking. Do you guys understand that? Nick's speedy today. Are the rest of you guys speedy? He said it doesn't pass the vertical line test. It wouldn't be a function then, right? Do you guys see that? So if you ever have it in that bottom part there, you're not going to have anything in that part above. So it's not going to be there. So let's plug in one more point, and we're going to plug in a point that's on the right of that vertical asymptote. So let's plug in 4. So when we plug in 4, we get 8 times 5 divided by 1. We get 40. Ooh, way up there. So way up here.
Where are you getting 8?
When I plugged in 4, I plugged in here. Yeah, I usually plug it in the factored form. It's easier for me to multiply than like keep track of all those numbers and add. So that means that it is indeed over here. And then just make sure there were no holes, right? So we don't have to draw any holes at the very end, so we're good. Okay, is this making sense? I know this is a lot. It's tricky. All right, so let's put it all together. So it says steps for graphing a rational function. So whenever I have you guys graph things on the test, I usually like break it up into pieces. So I'll say like find the x-intercept, find the y-intercept, find the, whatever you need to find. So we're doing the same thing here. So we're going to find x and y intercepts. We're going to find vertical and horizontal asymptotes, slant asymptotes if possible. And then we're going to sketch everything in and use a t-table for extra points if needed. Okay. So step 1, I guess I should really make my steps more like I actually do it. So step 1 is I always factor. So let's factor first. So I'm going to factor in the numerator and denominator. So I pull out that 3, and I have x squared minus 4 when I do. And then I factor the bottom into x minus 3 and x plus 1. So I get 3 times x plus 2 times x minus 2 all over x minus 3 times x plus 1. So do I have any holes, first of all? Yeah, no holes. So let's start with the asymptotes. So our vertical asymptote, so Jacob, what are you saying? Yeah, because we set our denominator equal to 0. So we have x minus 3 equals 0, and we have x plus 1 equals 0. So we get x equals 3, and x equals negative 1. So we have both of them. So we're going to have 3, so dotted line of x equals 3, and negative 1, dotted line there. Horizontal asymptote. Yeah, we're going to do our shortcut. So look for your largest degree. So we had 3x squared minus 12 all over. You don't have to write all this out if you guys know the shortcut already. But we look for our largest degree, which is 3x squared, and divide it out. 3x squared over 1x squared is 3 over 1, which gives us 3. So y equals 3 is our horizontal asymptote. So now let's find the x and y intercepts. So x-intercept. So just like when we did the equations of lines, we plug in 0 for the y. So we're going to have 0 equals, and I'm going to use that factored form, so I'm going to say 3 times x plus 2 times x minus 2 over x minus 3 times x plus 1. So I factored it completely. So let's think about it. If I have a fraction, so this is all of one big fraction, and if that fraction is equal to 0, is the numerator equal to 0 or is the denominator equal to 0? Yeah, what do you guys think? Numerator? Yeah, does it make sense? Like 0 divided by 7, what's 0 divided by 7? 0, right? What's 7 divided by 0?
Undefined.
Yeah, we don't know, undefined, right? So we want the numerator to be equal to 0. So basically what I tell my students every year is it's kind of like you're multiplying that part over, and it's all going to be 0 anyway, right? It's going to go away. So imagine you're multiplying that over and it goes to 0 anyway. So really, when we plug in 0 for y, we're setting our numerator equal to 0. So if that had just been like a 1 on top, if I had like 1 over x minus 3 equals 0, then is there any x-intercept? No, because my numerator, 1 equals 0, doesn't work. I can't set my numerator equal to 0. So I think you guys have things like that on your homework. And every year people are like, wait, what about my x-intercept? You may not have an x-intercept. Okay, so our x-intercepts here are going to be x equals negative 2 and x equals 2. So it's a point, negative 2 comma 0 and 2 comma 0. So we have these 2 points.
What
Okay.
about
The 3?
on the outside?
Oh, the 3 doesn't matter because like 3 equals 0 doesn't work, right? If 3 is equal to 0, then there's nothing that you're gaining there. There's no x there. All right, so right now, I kind of know what happens on this left-hand side. Can you imagine what's happening here? It's going along the vertical asymptote, and then it has to curve to go along that horizontal. Do you guys see it? So I can at least sketch in what's happening on the left-hand side of the graph. So I know it has to do that. It has to go along the vertical, can't cross a vertical. I could cross a horizontal, but not on the end of it. So when it makes this little like H shape with our asymptotes, like we know what's happening on those sides, right? Okay, but in the middle, we don't know what's happening. Okay, so let's find the y-intercept. So y-intercept, we plug in 0 for x. Okay, so who else have I not heard? How about Olivia? What do I get when I plug in 0 for x, for 0 for all of these? Yep, we get 4, exactly. We get negative 12 divided by negative 3. So we plugged in 0 for x. And we got 4. So that's going to be the point 0, comma 4. So do we cross this? Yeah, we definitely cross it. Do you guys see that it crosses? So we got to connect those in between there. So it's going to go along the vertical asymptotes. And last step, we still need to know what's happening on the right side of the graph. So do you guys see how it's a function so far? I don't have anything failing the vertical line test. But it's like, as we do the lines, we're like, okay, we got stuff here, we got stuff here, we got stuff here, but then what about over here? We don't have anything over here, right? So we need to figure out what's happening on that far right of the graph. So that's where I would do a quick little t-table, and any points that I'm missing, I would plug in. So I want to know what's happening on the right side of that vertical asymptote. So this was at x equals 3. So what should I plug in? 4, right, let's plug in 4. And I usually plug it into the factored form. So 3 times 6 times 2, 3 times 6 times 2, 36, over 4 minus 3 is 1, 4 plus 1 is 5, so 5, I think that's like 7.2. So it's way up there at 7.2. So way up here. So is that enough to tell us what happens on this side? Yeah, it's going to go along the vertical, and then it has to curve to go along that horizontal. So that's our graph. No holes, so we're done. Okay, so do you guys understand this? It's kind of weird. Let's pause, and you guys can go on your break, and then come back and be ready for this next one.
What exactly are the VA and HA? I'm not sure I understand.
All right, so let's do the very last example. So it says sketch the graph of x squared minus 4 over x squared plus 5x plus 6. Okay, so step 1, we're going to factor the numerator and denominator. So we have x plus 2 times x minus 2. And then we factor the bottom, it goes into x plus 2 times x plus 3. So does this one have a hole?
Yes.
Yeah, so someone besides Nick. Where's the hole? At x equals what? At x equals -2. Okay, so -2 is where the removable discontinuity is going to be. Okay, so we now graph the simplified version. Okay, so our simplified function is y equals x minus 2 over x plus 3. Okay, so we don't worry about that other function at all. Okay, so we're not going to go back there. Okay, so now we answer all of the questions based on the simplified version. So we answer our vertical asymptotes. So do we have vertical asymptotes? Yeah. Nat, put your phone away. So we get x equals -3. All right, do we have a horizontal asymptote? Yeah, so we do our shortcut method. So we have 1x over 1x, right? So 1x over 1x is going to be 1, right? So we have y equals 1. So we start to sketch that in. So we have x equals -3, and we have y equals 1. Are you guys good? So the next step, we're going to find the x-intercept and the y-intercept. Are you guys okay? You guys are doing something. It's making me mad. All right, the x-intercept. All right, so our x-intercept is going to be plugging in 0 for the y. So if we plug in 0 for the y, then we get 0 equals x minus 2 over x plus 3. So remember, this is where I told you that denominator doesn't matter. We can multiply the denominator over. So when we multiply that denominator over, it kind of goes away. So we're not worried about the denominator at all. We're just worried about that numerator. So we're going to have x equals 2. So that's a point. That's 2, 0. We plugged in 0 for y and got 2 for x. All right, so then the y-intercept, we plug in 0 for x. So again, in the simplified version, so if I plug in 0 for x, I get 0 minus 2, 0 plus 3. -2/3, exactly. So -2/3 is somewhere around there. So do you guys understand what's happening on the right side of the graph? Can you guys see it? Manish, do you have a juicy note back there? You do. Teachers still know all the gossip, by the way. We still know all the stuff happening because you guys talk loudly. We go to our desks, and you think that our ears turn off when we go to our desks? It's a juicy note. Is that what it says? Juicy note.
I
Awesome.
received one too.
Yay, good.
I got one.
That's exciting.
Joey, what do you give it?
Oh, I want juicy notes so bad. All right. Okay. All right, anyway, so we still hear what you guys say because we go to our desks and you guys think that teachers' ears turn off and then you guys start talking about things and I'm always like, oh, I didn't know that. Okay. So we still hear things. All right, so anyway, so -4. So I want to know what's happening on the left side of the vertical asymptote, right? So I want to do one little number in my t-table. I want to plug in that -4. So something over here. So if I plug in -4 into that simplified version, I get -4 minus 2 over -4 plus 3. So I have -6 over -1, which is 6. Yep. So -4, comma, 1, 2, 3, 4, 5, 6. And then we know that it goes along the vertical, along the horizontal, and we are almost done. Yeah, you're fine. Go. You're fine. So the very last step on all of these is if you have a hole, we put it in at the very end. So Greta was doing this during the break, and she was like, oh, so the hole at -2, so it's just going to go like right here along the x-axis. It doesn't go along the x-axis. It goes on the curve, wherever your curve matches up with -2. So we go down here, and then like right there, we're just going to draw in a hole. Does that make sense? Do you guys see it? So we have a hole at x equals -2. So if you can do all of those steps, you can do your homework. Okay, so let me pass out your homework.